The purpose of this example is to demonstrate how to calculate normal stresses in non-rectangular beams. To this end, we consider a concrete beam with a T-section. The beam is supposed to sustain a uniformly distributed load, and the strength of beam in compression is 20 MPa and in tension is 4 MPa. Our task is to determine what is the maximum uniformly distributed load Q the beam can support. We begin analyzing this problem by drawing a free body diagram for the entire beam and calculating the reactions. Because the beam is symmetric, the reactions share the load equally. The total load is 6Q expressed in newtons, and therefore each reaction is equal to 3Q. Next, I can use the free body diagram to construct shear force and bending moment diagrams. These diagrams are shown here, and I encourage you to construct them on your own. Here, I would only like to go over some highlights by convincing you that the shear force and bending moment diagrams are consistent with the free body diagram of the entire beam. Let me start with the shear force diagram. I start with 0 because there is no shear force or applied load applied at the left end. And then I proceed with the slope negative Q, which brings me to the force minus Q. Then there is a jump of magnitude 3Q up, which brings the shear force to 2Q. Then again, I proceed with the slope of minus Q for 4 meters. That brings me from 2Q to minus 2Q. Again, I have a jump, and again, I move with the slope negative Q, and I arrive at 0, which is consistent with the fact that there is no load applied at the right end of the beam. Now, if I look at the bending moment diagram, I start with 0. There is no couple on the left. Then the load is parabolic, and the magnitude at this end, minus Q over 2, is exactly equal to the area of this little triangle. The gain from minus Q over 2 to 3Q over 2 is exactly equal to the area of this triangle. Then the drop from 3Q over 2 to minus Q over 2 is equal to the area of this triangle. And finally, the gain from minus Q over 2 to 0 is equal to the area of this triangle. Again, I like this 0 because there is no couple applied on the right end of the section. Let me mention that the units on these diagrams are consistent with the notion that Q is measured in Newton over meter, so that the shear forces are measured in newtons and the bending moments are measured in newtons times meter. Next, we need to talk about analyzing the cross-section. We begin with identifying the centroid of the cross-section, and to this end, we identify the flange with the first subdomain and the web with the second subdomain. We also introduce the axes Z prime and Y prime. This choice is absolutely arbitrary. I choose Z prime at the top so that all Y primes are positive. And now I would like to calculate the centroid of the cross section in the coordinate system Z prime, Y prime. To this end, I calculate the centroid of the web and the flange and the areas of the web and the area of the flange. Now I can use these quantities to calculate the centroid of the entire cross section using coordinates y prime and z prime, and that's the standard formula, and according to this formula we obtain that the centroid is located at a distance 3.5 centimeters down from the z prime axis. My next step is to calculate the moment of inertia. To this end, I will redraw the cross section and show now the axis z and y, and of course the origin is now at the centroid, and I also mark 3.5 centimeter, which is the distance from the top to the z-axis within the cross section. Now, with this information in mind, I can recall that the areas of the flange and the web are 48 and 16 centimeters squares respectively, and I can now use the parallel axis theory. Let us go slowly over this result. First, I look at the flange. The moment of inertia of the flange with respect to its own axis is simply 12 times 4 cubed divided by 12. So it's bh cubed over 12 applied to the flange, plus the term that follows from the parallel axis theory. 3.5 minus 2 is the distance between the z-axis of the entire cross-section and the z-axis of the flange. 3.5 minus 2 squared times 48, the area of the flange. Now I go to the web. 2 times 8 cubed divided by 12. That's the moment of inertia of the web with respect to its own z-axis. 8 minus 3.5 is the distance between the z-axis of the web and the z-axis of the entire cross-section, and 16 is, of course, is the area of the web, and as a result we get that's the answer for the moment of inertia measured in centimeters to the fourth. Now we're in a position to calculate normal stresses in the cross section. We use the standard formula, and now we would like to redraw the cross section, emphasizing the difference from the neutral axis to the top and to the bottom of the cross section. This really become the critical dimensions now. From the bending moment diagram, I obtained that the most negative moment or the minimum moment is minus half q, and the maximum or the most positive moment is 3/2 q, again measured in newtons times meter. The minimum y also represents the distance to the upper fiber, and the maximum y the distance to the lower fiber, please pay attention that I converted these values from centimeters to meters. Then I need to record the moment of inertia. Again, converted now into meters, and the strengths in tension and compression. And these two values were given to us. We can use this information to calculate force stresses. And let me proceed to that part of the problem. So first, I will consider the cross section in the middle of the beam where the moment is equal to 3/2 Q and it is positive. Because the moment is positive, the upper part of the cross section in compression and the bottom part is in tension. And then I calculate the maximum stress in this cross section at the bottom using y equal to 0.085, and at the top using y equal to 0.035. And of course, I compare the stress to the strengths in tension and the stress to the strengths in compression. And this results in the values of Q's given here. I will repeat this calculation, but for the cross section where the bending moment is negative. So this is just about the supports. In this case, the top is in tension, the bottom is in compression, and I repeat the calculations with using 0.35 again for the red zone and 0.085 for the blue zone, and I compare them to the maximum allowable stress in tension, maximum allowable stress in compression, and now I have four numbers, four values of Q. Obviously, in order for the beam to be safe, I must choose the lower value of Q, which is clearly 182 newtons per meter. So the important lesson in this beam is because of asymmetry of the beam and because of the difference in tension and compression, we have to consider force stress calculations. In contrast, if I consider a rectangular metal beam where we don't have asymmetry in geometry and also we don't have significant difference in tension and compression, one stress calculation is good enough. Next, and finally, I'd like to ask a very natural question. Is it a good beam? To analyze, or to better say, answer this question, I will simply say, let me take the maximum allowable load on this beam, 182 newtons per meter, and compare this Q with QW, which is the uniformly distributed load to the beam weight. To calculate this load, I use the definition that this is the weight per unit length. The unit length is denoted by delta S. The weight is the specific weight of concrete times the unit volume. And as a result, I obtain that QW induced by concrete is equal to gamma concrete times A, where A is, of course, the cross-sectional area. A has been already calculated, and gamma concrete we can get from a handbook, and the good value is 23 kilonewtons per meter cube. If I take these two numbers and multiply them, I'll obtain that QW is 147 newtons per meter. Clearly, this is a very bad beam because it can barely sustain its own load, right? And 80% of Q will be taken by the load. So a horrible beam. Thank you.